Hi, my name is Josh Hardesty. I'm from the University of Oklahoma, and this is my first bi-weekly report. I'll be doing Raman spectroscopy of ammonium nitrate and sodium nitrate in water. Oh, and they're working under Dr. Shaw. So what is Raman spectroscopy? You guys heard about this in the first day we were here at the REU. Lasers, electrons have different energy levels, and so when a laser is shown at an electron cloud, it can boost, if it absorbs enough energy, it boosts it to its next energy level. And a certain amount of energy is needed for the electron to be boosted to that level. In Raman spectroscopy, a laser is pointed at a sample, and it absorbs energy, and the electron is boosted to another energy level. Well, when the electron comes back down, it also shoots off a photon, and that photon is at a different frequency, and therefore different energy than the original photon that was accepted into the electron cloud. And this shift can be measured. A bit of history. Raman was actually not the first person to discover it. Adolf Schmeckel was. And he actually found it, I don't know, he found it, Raman found it, and then these other guys, Grigory and Leonid, also found it independently of him. I don't know the specifics, but Raman ended up getting the Nobel Prize for it. And Raman spectroscopy is the fingerprint a molecular fingerprint of a substance, in that its spectroscopy is very unique to that substance. And what I've done so far, we're kind of running two experiments. One is using ammonium nitrate, another one is using this sodium nitrate. And for ammonium nitrate, we are putting it and mixing it, dissolving it in water, and then we're measuring from different distances, such as 1 meter, 2 meter. I'm actually doing 1 through 5 meters, not just 2 meters, 3 meters, 4 meters. And the second experiment we're doing is Raman spectroscopy with different concentrations in water. At the time, we're actually doing a much more concentrations than 1,000 and 2,000 parts per million. At the time, that's how many we have. But basically, we shine. This is like a little cartoon. A laser. This is actually supposed to symbolize the Raman spectroscopy apparatus. And we shoot a laser, hit it off the mirror into our substance. And then when the laser hits the substance, all the electrons, the photons, get emitted. But they're emitted in every direction. And the photons that this picks up is only that small amount. So whatever the photons pick up is a function of the distance from the sample to the detector of distance squared. And so this is just a spectroscopy of a normal ammonium nitrate powder. The powders gives very distinct peaks. This one in the middle is actually the nitrate. They're just little samples we've taken from different distances, 2 meters, 3 meters, 4 meters. And they all kind of look the same, but the problem is that it doesn't look anything like that. You can see little small peaks at the 1,000 in each of these. But part of my job over at the RU will be to figure out what all this means. For example, what these peaks are that keep showing up in our measurements. This one's for sodium nitrate. It also has the large peak in the middle, except these two peaks are different. And here's for the different concentrations. They look very similar, and as of now, I think that is because of the both nitrates. Nitrates seem to be very prominent peak in Raman spectroscopy. So what are my goals for the rest of the RU? One of them is to find and catalog the meaning of all these different peaks, and actually be able to look at a graph and be like, oh, this means that this substance is in this sample. And applications. Part of the reason we're using ammonium nitrate because it's for military applications. If you shine a laser at something like a liquid that came in contact with explosive ammonium nitrate, then you know, just finding this trace of ammonium nitrate means there's explosives on it. And Raman spectroscopy in general has applications in Homeland Security, just detecting, for example, when you go to the airport space, you can't have water, right? Because it could be a potential explosive. Using the microscopy, you could clearly detect that what is water and what's not water. Drug detection and astrobiology. And this one professor was doing a project where he would take the microscopy of methane, and you can send things, like attach it maybe to like a Mars rover, and just be able to take a sample of the atmosphere. Questions? Comments?
What current theories do you have about the peak between 15 and 1600?
I don't know yet, but it has something to do with sodium or ammonia, not nitrate.
Could it have something to do with the lens?
Oh, right, that peak, I'm sorry. Also, some peaks, we've been told, it could be the lens, like different materials in the lens that they see. Yeah.
Did your research compensate for any background radiation and background noise?
That's kind of what we want to try and see if what we see is background or if it actually has meaning to the sample.